A warm greetings from Rohini College of Engineering and Technology. I am Professor Radhika, Department of Chemistry. In this video lecture series, we discuss about two component system of phase diagram. In this previous video, we discussed about the terms involved in the phase diagrams as well as the one component system. After the completion of this topic, students can able to explain the importance of phase diagrams in the field of material science and engineering. Let us see the two component systems. So we know that in a two component system, we use condensed phase rule or reduced phase rule. Y means when the system exists in a single phase, the maximum number of degree of freedom in a two component system will be 3. In order to represent the condition of equilibrium graphically, we need 3 coordinates, namely temperature, pressure and concentration. But it is somewhat difficult to draw the graph at a paper. Therefore, we have taken any two of 3 variables for a graphical representation. Let us consider a solid liquid equilibrium of an alloy. It has practically no gaseous phase. The effect of pressure is negligible in that case. Therefore, the experiments are conducted under atmospheric pressure. Therefore, the system in which only the solid and liquid phases are considered and the gas phase is ignored is called as a condensed system. Here, the pressure is kept constant. Therefore, the phase rule becomes F dash is equal to C minus P plus 1. This equation is called as reduced phase rule. Here, we consider only the solid and liquid phases alone. Gaseous phases are ignored. That's why this system is called as a condensed system or condensed phase rule. Let us see the phase diagram of two component system. The example given are lead silver system. Here the lead silver system is studied under constant pressure. Here the vapor phase is ignored. Therefore, we have used the reduced phase rule. F dash is equal to C minus P plus 1. This phase diagram consists of two curves, curve AO and curve BO. Similarly, containing one eutectic point O. Then areas below AO, below BO and below O. Let us see one by one. The curve AO. The curve AO is known as a freezing point curve of silver. The point A indicates the melting point of pure silver. Its the temperature is 961 degree centigrade. Along the curve AO at any point, the equilibrium exists between solid silver and melt. The curve AO shows the melting point depression of silver by the successive addition of lead. Therefore, along the curve AO, two phases are exist. One is solid silver and another one is a melt. Therefore, number of phases in this curve AO is 2, component is 2. Therefore, degree of freedom is equal to F dash is equal to C minus P plus 1. Therefore, F dash is equal to 1 univariant. Let us see the curve BO. The curve BO also known as freezing point curve of lead. The point B is the melting point of pure lead. 327 degrees centigrade is the melting point of lead. The curve BO shows the melting point depression of lead by the successive addition of silver. Along the curve BO, that is any point along the curve BO, the equilibrium exists between solid lead and melt. Therefore, the number of phases is equal to 2. Degree of freedom is equal to 2 minus 2 plus 1. Therefore, F dash is equal to 1 univariant. Let us see the point O. Point O is called as a eutectic point. The curve AO and BO meet at one point. That point at a temperature of 303 degrees centigrade, where all the three phases like solid Ag, solid lead and liquid melt are in a equilibrium. Therefore, here the system exists in a non-variant. Component value is equal to 2, P value is equal to 3. Therefore, by applying reduced phase rule, F dash is equal to 0, non-variant. The point O is called as a eutectic point. The temperature related to this eutectic point is called as a eutectic temperature. At this point, the composition's values are 97.4 percentage of lead and 2.6 percentage of silver. This composition is called as a eutectic composition. Then areas. Area above the line AOB consists of only one liquid melt. Therefore, applying the reduced phase rule, F dash is equal to C minus P plus 1. Therefore, substitute P value is equal to 1, C value is equal to 2. Therefore, F dash is equal to bivariant. Here, the temperature as well as composition have to be specified to define the system completely. Similarly, the area below the line AO, below the line BO and below the point O consists of two phases. Therefore, the system is univariant. Similarly, let us discuss about the applications of partition process for the desilverization of argentiferous lead. So, argentiferous lead containing a very small quantity of silver, approximately 0.1 percentage, which is heated to a temperature above its melting point. Therefore, the system containing only one liquid phase, which is represented by the point P in the diagram. It is then allowed to cool. What happens means the temperature is gradually fall down along the line PQ. As soon as when the point Q is reached, the lead is crystallized out and the solution will contain relatively increasing amount of silver. And further cooling, more and more amount of lead is separated along the line BO and the melt continues to be richer and rich in silver until the point O is reached, where the percentage of silver is raised to 2.6 percentage. Therefore, the process of raising the relative proportion of silver in the alloy is called as a Pattinson process. Thank you for listening.